So today what we want to look at is the fundamental theorem of calculus. Now, anytime something is a fundamental, it's probably pretty important, okay? And the reason why this is important is because finally, we're going to be able to do a lot of our integration over an interval, our definite integration, without having to use the limit of the sum and do all that mess, okay, with the Riemann sums. We're going to be able to basically write down our answer, which will be really, really nice. So let's take a look at what the fundamental theorem of calculus says and what it does for us. Okay, so this says let capital F be the antiderivative of f. We already talked about antiderivatives. It says the integral from a to b of f of x dx equals, and then you see this notation here. It has the antiderivative in brackets with the a and the b next to it. Okay? So what does that notation here mean? That means we're taking the antiderivative and then we're going to evaluate it at b and we're going to evaluate it at a. And then you'll notice what that means is that we are going to subtract. Now, you'll notice here what happens is the plus c's will end up canceling each other out. Okay? So in this case, when you're doing definite integrals, you don't need to worry about writing down a plus c, because it's just going to cancel out anyways. But you're going to end up with the definite integral equals the antiderivative evaluated at b minus the antiderivative evaluated at a. And let me just explain to you what's going on here, okay? Let me draw a picture. Here we have a function, and the function, let's say, looks like this, okay? And here's a, and we'll do b in green here, and here is b, okay? Now, we want the area between these two, of course. Alright, so I'm actually going to do, I'm going to highlight that in blue here. Wrong one.
Oh, your fault.
Maybe someone is talking behind you. Yeah, because in business was 3 times and somebody is talking behind you.
Really?
Yes.
I only season 3s.
Yes.
Alright, so let's take a look at what is going on here. When you do capital F of b, alright, we're going to do this in green here. So capital F of b is going to give you an area, but notice what it's going to do. It's actually going to give you an area starting at b, and I don't know if you can see this highlighting really good, but it actually gives you the area all the way down to negative infinity. Okay? So it's giving you this area all the way down to negative infinity. Well, obviously we don't want all the area down to negative infinity. We only want it down to a. So that's why we subtract capital F of a. Capital F of a gives us the area from a all the way down to negative infinity. And you can see here now that eliminates the part that we don't want, leaving us with just the middle that we were looking to get. This area between a and b, the x-axis, and the function itself. Okay? So that's why we're doing this subtraction, f of b minus f of a. Now there's a big old proof to this we're not going to bother doing. you do calculus in college, you'll probably learn the proof, maybe even have to memorize or rederive the proof yourself, but we're not going to.
If we pass the AP calculus exam, you don't have to take calculus in college?
It depends what college you go to.
What if the college lets me take calculus and I don't pass the test, I pass the test for AP calculus BC?
Alright, so that's what's going on. So let's do a couple of examples and see how this works. It's actually a really easy process, especially when you compare it to doing the limit of the sum. Alright, so here we have the integral from -1 to 2 of 3x squared plus 2 dx. Alright, so first thing we have to do is we need to find the antiderivative. Okay, so the antiderivative, capital F of x, for 3x squared plus 2 is what?
X, 3x cubed.
Okay, 3x cubed over 3 plus
Plus 2x.
plus 2x.
Plus c.
Alright, so that's going to cancel. So this is going to be x cubed plus 2x plus c. Now, we don't really care about the plus c here because as we saw above, when you do a plus c and then minus c, that's going to cancel out. So we don't need to worry about it here. Okay? So, just to look at the notation, we would put x cubed plus 2 like this, and we would go from -1 to 2. That's the notation here. Now, you may also see, depending on if you're looking at a particular website or a different book, you might see it as x cubed plus 2, whoops, I lost my x, and you might just see it on one side like this, or you might even see it written just with like a hard vertical line like that. Okay? They all mean the same thing. We're using the fundamental theorem of calculus and evaluating it twice. Okay? So, at this point here, we're going to plug in 2. So we get 2 cubed plus 2 times 2. And then we're going to subtract it after we plug in a -1. So -1 cubed plus 2 times a -1. Okay? So we have a 8 plus 4 is 12, minus a -1 minus 2 would be a -3. So the area here is 15. I believe this is the exact same example we did yesterday, using the limit of the sum. Remember our warm-up yesterday? And we ended up getting 15.
I think they are all the same actually.
Okay. Well, the nice thing about this actually is that the process is going to be the same for all of these, okay? So in this example, we're seeing this as 3x to the 1/2. Remember too, you can, those properties that we learned yesterday, we can also do 3 times the integral from 1 to 4 of radical x, or I could say x to the 1/2 dx. Okay? Now don't forget to distribute the 3 or multiply by the 3 at the end, okay? But this is going to be 3 times what? What is the antiderivative of x to the 1/2?
X to the 1 over, no sorry, x to the 1.5 over 1.5.
Okay, x to, if you want to do decimals, that's fine. X to the 1.5 over 1.5, or it would be x to the 3/2 times 2/3. If you flip and multiply the 3 by the 3/2. but you're going to do this from 1 to 4. Okay? You can do this from 1 to 4. Now, one thing you may want to do, since you might see that it comes out nicely, you can distribute or multiply the 3 into this before we evaluate. Okay? It's all about what makes it easier for you. Alright? So, if I multiplied the 3 in, that would just simplify to 2x to the 1.5, evaluated from 1 to 4. Right? It's all a matter of preference of what you want to do. You can bring the constant in here, or you can wait till the very end. Now, if I'm doing the 1.5 power, how do we evaluate that?
Use your calculator.
Plug in.
3/2.
It's the 3/2 power. So if I'm doing 4 to the 3/2 power,
Square
So
root
it's
of.
4 times
Oh.
root 4. Isn't it square root of x cubed? Or 4 cubed?
it's the square root of 4 cubed.
Yeah.
Alright? It doesn't matter whether you do the square root first or the cube first. Do whichever one's easier.
Oh, so is it 8?
Okay? So yeah, this one comes out to be, if I do the square root first, that means it's now 2 cubed. So that's 2 times 8. Okay? Now I still need to subtract this evaluated at 1. It's going to be 2 times 1 to the 3/2, which is just 2 times 1, which is 2. So now we have 16 minus 2, and that definite integral equals 14. Okay?
Literally, how are you getting such a perfectly rounded value?
Because the problem was set up really nicely for us.
Well,
It's not always going to happen that way. But yeah, we started you with some that come out a little bit nice. Alright, let's do another one with a trig. Okay. What is the integral of secant squared?
That's gonna be no from here.
Secant times tangent.
Tangent.
Tangent. Remember, the derivative of tangent is secant squared. So the integral of secant squared is going to be tangent. The secant tangent was the derivative of secant. So if you're taking the integral of secant times tangent, it'll equal secant. Okay? So the better you know those derivative rules for your trig functions, the easier integration will be. Okay? So this is simply tangent of x evaluated from 0 to pi over 4.
The derivative of 10 is sec squared, right?
Yes, the derivative of tangent
Is sec squared, okay.
equals secant squared. That's a rule we learned a while back.
Yeah.
So that means the integral of secant squared of dx is going to be tangent of x plus c. Okay? So, I'm doing tangent of pi over 4 minus tangent of 0. What's tangent of pi over 4?
1.
1. Very good. It's 45-degree angle, so it's root 2 over 2 over root 2 over 2 on our unit circle, which we all know really well. Right?
You know that
Okay.
the pre-college students are taking a test on unit circle today.
Huh?
The pre-college students are taking a test on unit circle today.
Yeah, they had to learn it. You had to learn it in pre-calculus, so
Yeah.
we should still know it now. So,
You don't.
what's tangent of 0?
0.
0. So this whole thing just equals 1. Okay? So that's not too bad, right? That's our fundamental theorem of calculus. Take the antiderivative, evaluate it at the upper bound, evaluate it at the lower bound, and subtract the upper minus the lower. Let's look at two applications here that we can use, alright? We have, in this case, evaluate the integral from 0 to 2 of the absolute value of 2x minus 1. Okay? So when you have this, you have to rewrite the function, okay? So a sketch would be helpful here. The absolute value of 2x minus 1, we have the line
You can just
2x minus 1, okay? By the way, these absolute value ones, it might be helpful to sketch it without the absolute value. Here's negative 1, I go up 2 over 1, okay? So here's the line if I did not have absolute value, y equals 2x minus 1. If I'm doing the absolute value of 2x minus 1, then right here at 1/2, 0, it's actually going to bounce back up, okay? So there is y equals the absolute value of 2x minus 1. Okay? Does that make sense? Now, that's useful because notice if I want to do the integral from 0 to 2, I'm going to need to look at two different pieces, all right? And that's where, okay, if f of x is the absolute value of 2x minus 1, I'm going to need to rewrite this as a piecewise function. As we can see, for any x's greater than or equal to 1/2, we can just stay on the line 2x minus 1, right? But if I am less than 1/2, what am I going to have to be on?
the opposite.
Negative.
Yeah, it's going to be the opposite, negative 2x plus 1. Okay? So I rewrite this as a piecewise function, and then I can take the antiderivative, okay? Capital F of x is going to equal one thing if x is less than 1/2, and another thing if x is greater than or equal to 1/2. Okay? What's the antiderivative when x is less than 1/2?
Negative x squared.
Negative x squared
Plus x.
plus x, okay? Negative 2x squared over 2, so it's a negative x squared plus x. What is it going to be when x is greater than 1/2?
X squared minus x.
X squared minus x, okay? So notice here, when I do the fundamental theorem of calculus, all right, if I'm going from 0 to 2, which takes me from here to here, how could I have done this without the fundamental theorem of calculus?
The area underneath between 1/2 and 1.
Mm-hmm.
And underneath that, and then add it to the area between 0 and 1/2.
Using triangles.
Yeah, I could use areas of triangles. Yeah, find the areas here. Okay? So now the question becomes, do I need to break this into two separate parts? Do I need to do the integral from 0 to 1/2 of, that would be negative 2x plus 1 dx, plus the integral from 0 to 2 of 2x minus 1 dx? Or can I simply take capital F of 2 minus capital F of 0 using this?
That one.
Okay? Let's see. If I plug in a 2, that means I need to use the x squared minus x, right? So if I do x squared minus x, that's going to be 2 squared minus 2. Then I subtract f of 0. Well, 0 is when I plug in the, I'm going to have to plug that into the top part because x is less than a half,
So
right?
it's negative 0 squared plus 0.
So negative 0 squared plus 0, which obviously is 0. Alright, so that's 4 minus 2, which is 2. Let's see if we get exactly the same thing over here. Over here we would have had a negative x squared plus x evaluated from 0 to a half plus the x squared minus x evaluated from, oh wait, not 0 to 2, 1 half to 2. Okay? Let's see if we get the same thing. Alright? So if x is a half, I get a negative 1/4 plus 1 half minus 0. That's f of b minus f of a. So that's going to be 1/4 plus, if I have from 1 half to 2, I plug in the 2 first, so that's 2 squared minus 2, minus this plugged in at a half, which was negative 1/4 plus a half. Okay, so that's 2 minus 1/4, and what do you know? The 1/4s cancel out and we have just 2. So in both ways, we just got 2 as the value of the integral. Okay? So I did both of these just to show you when you have something like this, you don't have to break it up into 2 separate integrals. You can simply take capital F of 2 minus capital F of 0, and again the reason is because you defined it as a piecewise function, okay? And in both cases, here you had capital F of a half minus capital F of 0. Here you had capital F of 2 minus capital F of a half. You had capital F of a half minus capital F of a half. So those canceled out. Alright? So, again, don't make your life too difficult by doing extra work. Alright?
But in this case, if you
Just to show you what I was just pointing out on the board. Capital F of 2 minus capital F of a half. Notice here the, whoop, not that one. The f of a half minus f of a half is 0, and you have the f of 2 minus f of 0. And that's all that's left. Okay? Okay, one last example here. Find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis, and the vertical lines x equals 0 and x equals 2. Area bounded, we would need to look out for parts where it might go under the x-axis and make that part positive. But in this case, note that y is always greater than 0 for the region we want. Okay? So just to highlight what we're looking for, here's our function. Here's the x equals 0. Here's x equals 2. And we want this area bounded by that. And the x-axis. So what is this problem really asking us to do? Find the definite integral from 0 to 2 of the function 2x squared minus 3x plus 2 dx. Okay? try this one, take a couple minutes here, try this one on your own, and then we'll see how you can do. So let's look at our solution here, okay? First of all, what is the antiderivative that we are evaluating?
So it's 2x cubed
Mm-hmm.
divided by 3
Good.
minus 3x squared to second
Over 2, okay.
and to plus 2x.
Plus 2x. Okay, so that is what we are evaluating from 0 to 2. Okay? Now, the nice thing about this is, what do you get when you plug in 0?
0.
0, okay? So we're going to evaluate this at 2, and then we know it's going to be minus 0, because if you plug in 0, it's 0. So what do you guys get when you evaluate it at 2?
10 over 3.
10 over 3?
Yes.
Okay, so yeah, you'd have 16 thirds minus 3 times 4, that's 12 halves, plus 2 times 2 is 4, okay, so that's all capital F of 2, so you have 5 1/3 minus 6 plus 4 is 3 1/3. Okay? So that's our area. Any questions? Okay.